Carbohydrates are initially synthesized in plants by photosynthesis. In biochemistry, the carbohydrates is a synonymous of saccharide. The word saccharide comes from the Greek word saccharon, which means sugar. The term carbohydrate often means any food that is particularly rich in complex carbohydrate starch, such as cereals, bread, and pasta, or simple carbohydrates such as sugar. It is found in candy, jams, and bar. And the carbohydrate is composed of water and carbon. The carbohydrates are important for provide energy, store energy in the form of starch. It is found in plants, and glycogen, it is found in animals and humans. Supply carbon for synthesis of other compounds and form structural components in cells and tissues. The classification of carbohydrates. The carbohydrates are hydrocarbon molecules or carbon and hydrogen that are classified into monosaccharides, cannot be hydrolyzed. The disaccharides on hydrolysis give 2 monosaccharides. Oligosaccharides on hydrolysis give 3 to 10 monosaccharides. The polysaccharides on hydrolysis give 10 or more monosaccharides, and complex sugars on hydrolysis give us sugar molecule and non-sugar molecule. Disaccharides. The disaccharides are the carbohydrates that are made up of 2 monosaccharide subunits. They act as a source of monosaccharides. Sometimes they also used as an alternative to monosaccharides as they share various common properties. The formation of a disaccharide. As mentioned earlier, the disaccharides are made when 2 monosaccharide subunits are combined. The 2 monosaccharide molecules are attached via a glycosidic bridge or bond to form a disaccharide. As the water molecule is released in this process, it is also known as a dehydration reaction. The structure of a disaccharide is much similar to that of a monosaccharide. They also consist of a multiple hydroxyl groups and a functional group that could be an aldehyde or a ketone. The only difference is the presence of a glycosidic bridge connecting the 2 molecules. The glycosidic bridge or bond is the 2 carbon atoms of 2 different molecules joined using an oxygen atom. The oxygen atom acts as a bridge connecting the 2 different carbons of 2 different monosaccharide molecules in a glycosidic bond. The importance of a disaccharides are the maltose, lactose, and sucrose. The maltose, it is used in brewing. It is composed of glucose and glucose. The lactose is transport sugar in milk. It is composed of glucose and a galactose. And the sucrose, it is transport sugar in plants. It is composed of glucose and fructose. Sucrose. Sucrose is the most important carbohydrate belonging to the class of disaccharides. It is also known as table sugar or cane sugar. Its molecular formula is C12H22O11. The structure of a sucrose. It is made up of a glucose and the fructose molecule joined together by a glycosidic bond. This glycosidic bond is formed between the carbon 1 of glucose and the carbon 2 of fructose. It is formed between the functional groups of 2 molecules. The fructose molecule in sucrose has a beta orientation, while the glucose molecule has a alpha orientation. In alpha orientation, the OH group of the anomeric carbon is oriented on the side of the ring opposite to the side of 6th carbon. On the other hand, in beta orientation, the OH group of the anomeric carbon is on the same side of the ring as the 6th carbon. The anomeric carbon is the carbon atom of the aldehydic or ketonic functional group. Thus, the glycosidic bond in sucrose is called alpha-1 beta-2 glycosidic bond. Properties of sucrose. Sucrose is sweeter than glucose. It is soluble in water. It is a white crystalline solid in appearance. It is non-reducing sugar because no free functional group is available to act as a reducing agent. It is dextrorotatory, meaning that it can bend light in the right direction when passed through it, and also it yields glucose and fructose on hydrolysis. Sources. Sucrose is mainly obtained from fruits and nectars. The amount of sucrose is high in the ripening fruits, but it decreases as the fruits are ripened. Sucrose is present in large amounts in sugarcane. This is the reason why it is also called cane sugar. Digestion. In the human body, sucrose is digested in the small intestine by an enzyme called invertase or sucrase. This enzyme breaks sucrose into glucose and fructose molecules that are absorbed in the blood and carried to the liver for metabolism. Uses of sucrose. It is used as a table sugar. It is used as a sweetening agent in confectionery and desserts. It is used to make inverted sugar syrup. Inverted sugar syrup is made when sucrose is heated in the presence of water. It consists of glucose and fructose in equal amounts that are not chemically bound together, and it is more commonly used in industries as a sweetening agent because it is sweeter than sucrose, glucose, or fructose. Lactose. Lactose is another important disaccharide commonly consumed by human beings. It is also known as milk sugar. Its molecular formula is the same as of sucrose. Structure of lactose. Lactose is made up of glucose and galactose molecules attached via a glycosidic bond. It is a C1 to C4 glycosidic bond as it attaches the first carbon of glucose to the fourth carbon of galactose. Both the glucose and galactose molecules have alpha orientation in lactose. Therefore, the glycosidic bond between them is also called alpha 1 to 4 glycosidic bond. Lactose is a crystalline white solid having the following properties. It is soluble in water, but its solubility is less than sucrose. It is less sweeter than sucrose, and also it is also dextrorotatory, rotating light's ray to the right. Sources. Contrary to sucrose, lactose is purely animal in origin. It is only made by the lactating mammary glands of mammals. The enzyme necessary for its synthesis is only active during the phase of lactation. Lactose is the most abundant sugar found in milk, and milk products like cow milk, goat milk, human milk, and etc. Digested. It is digested in the human body by lactase enzyme present in the small intestine. The glucose and galactose molecules are then sent to the liver for further metabolism. Uses of lactose. It is used in infant formula milks as sugar. It is used in pharmaceutical industries as an ingredient, and also it is used in the beverage industry to sweeten stout beer. Maltose. Maltose is a disaccharide that is not abundantly found in nature. Its molecular formula is the same of sucrose and lactose. Maltose is a disaccharide made up of two subunits of glucose. Both the glucose molecules are attached via a 1 to 4 glycosidic bond. This bond attaches the carbon 1 of one glucose molecule to carbon-4 of the second glucose molecule. The first glucose molecule has alpha orientation. The second glucose molecule retains its aldehydic functional group and can have either an alpha or beta orientation. Properties of maltose. It is reducing sugar due to free aldehydic group of glucose. It is soluble in water. It has a sweet taste. Upon hydrolysis, it yields 2 glucose molecules. Sources. It is only rarely found in nature in some fruits. A major source of maltose is malt, which is obtained when the grains are kept in water for a long time. In the human body, maltose is formed during the digestion of starch. It is the major breakdown product of starch, digestion. Maltose can be digested in the human intestine by an enzyme known as maltase. Upon digestion, maltose yields 2 glucose molecules that are further processed in the liver. So, the sucrose is the common sugar made up of glucose and fructose. The sucrose is non-reducing sugar. It is present in fruits, berries, nectar, etc. It is used as a sweetening agent in homes as well as in industries, and also it is used to make inverted sugar syrup. The lactose is milk sugar present only in milk of mammals. It is made up of glucose and galactose, and lactose is a reducing sugar. The maltose is a less common disaccharide present in nature. It is a breakdown product of starch digestion. It is a reducing sugar made up of 2 glucose molecules, and it can be digested in the human body by maltase enzyme.
Enantiomers in monosaccharides. It is a special form of isomerism found in pairs of structure that are mirror images of each other. So what do you mean by isomerism? So isomerism is the phenomenon in which more than one compounds have the same chemical formula but different chemical structures. Chemical compounds that have identical chemical formula but differ in properties and the arrangement of atoms in the molecule are called isomers. So therefore, the compounds that exhibit isomerism are known as isomers. So the word isomer is derived from the Greek word isos and meros, which means equal parts. This term was coined by Swedish chemist Jacob. In the D-isomeric form, OH group on the asymmetric carbon, a carbon linked to 4 different atoms, farthest from the carbonyl carbon is on the right, while alloisomeric form is on the left. Enzymes known as racenases are able to interconvert to D and L organs, in D to L and L to D. Cyclization of monosaccharides. Less than 1% of monosaccharide with 5 or more carbons exist in the open chain acyclic form. The majority are predominantly found in a ring cyclic form in which the aldehyde or ketone group reacts with OH group on the same sugar. Anomeric carbon is a cyclization creates an anomeric carbon, which is the former carbonyl carbon, generating the A and B configuration of the sugar. For example, A to D glucose and B to D glucose, these two sugars are glucose but are anomers to each other.
Complex carbohydrates. Carbohydrates can be attached by glycosidic bonds to non-carbohydrates molecules including purines and pyrimidines in nucleic acid, proteins and glycoproteins, lipids and glycolipids. Isomers in epimers in monosaccharides. Isomers. Compounds that have the same chemical formula but with different structures. For example, fructose, glucose, mannose, and galactose are all isomers of each other having the same chemical formula of C6H12O6.
Oligosaccharides. Oligosaccharides, any carbohydrate from the 3 to 10 units of simple sugar or monosaccharides. A large number of oligosaccharides have been prepared by partially breaking down more complex carbohydrates or polysaccharides. Oligosaccharides can have many functions including cell recognition and cell bidding. Most of a few naturally occurring oligosaccharides are found in plants. Raffinose, a trisaccharide found in many plants, consists of melabiose or galactose and glucose, and fructose. So the function is serve as desiccation protectant in seeds, as transport sugar in phloem sap, and as storage sugars. So this is the structure of oligosaccharides raffinose, galactose, glucose, and fructose. Stachyose is a tetrasaccharide consisting of sucrose having an alpha D, galactosyl 1 to 6, alpha D, galactosyl mu attached at the 6th position of glucose. Function is recognized as a major storage and transport sugar in woody plants, cucurbits, and legumes.
Classification of monosaccharides. Monosaccharides are the simplest carbohydrates since they cannot be hydrolyzed to smaller carbohydrates. Chemically, they are aldehydes or ketones possessing two or more hydroxyl groups, and are important as building blocks for the synthesis of nucleic acids as well as fuel molecules that is in glycolysis. Monosaccharides are classified according to three different characteristics: the location of their carbonyl group, the number of carbon atoms they contain, and their chiral property. If the carbonyl group is an aldehyde, the monosaccharide is an aldose. If the carbonyl group is a ketone, the monosaccharide is a ketose. Monosaccharides with three carbon atoms are called trioses, and these are the smallest monosaccharides such as the hydroxyaceton and D and L-glyceraldehyde. Those composed of 4 carbon atoms are called tetroses. Those with 5 carbons are called pentoses. Those of 6 carbons are hexoses, and so on. Of glycogen and amylopectin of starch. A long chain of monosaccharides linked by glycosidic bond is known as a polysaccharide. The chain may be branched or unbranched, and it may contain different types of monosaccharides. The molecular weight may be 100,000 daltons or more depending on the number of monomers joined. Starch, glycogen, cellulose, and chitin are primary examples of polysaccharides. Glycogen is the storage form of glucose in humans and other vertebrates and is made up of monomers of glucose. Glycogen is the animal equivalent of the starch and a highly branched molecule usually stored in liver and muscle cells. Whenever blood glucose levels decrease, glycogen is broken down to release glucose in a process known as glycogenolysis. Amylopectin is composed of branched chains of glucose monomers connected by A1 and 4 and A1 and 6 glycosidic linkages. Because of the way the subunits are joined, the glucose chains have a helical structure. Glycogen, or not shown, is similar in structure to amylopectin but more highly branched. Starch is stored form of sugars and plants and is made up of a mixture of amylose and amylopectin, or both polymers of glucose. Starch is made up of glucose monomer that are joined by A1,4 or A1 and 6 glycosidic bonds. The numbers 1 and 4 and 1 and 6 refer to the carbon number of the two residues that have joined to form the bond. Cellulose is the most abundant natural biopolymer. The cell wall of plants is mostly made of cellulose. This provides structural support to the cell. Wood and paper are mostly cellulosic in nature. Cellulose is made of glucose monomer that are linked by B1 and 4 glycosidic bonds.
Monosaccharides. Simplest carbohydrate molecules are monosaccharide. Monosaccharides have 3 to 7 carbons, have either aldehyde group or ketone group, have hydroxyl groups on every carbon except carbonyl group. Polyhydroxyaldehydes or ketones are molecules with more than one hydroxyl group and a carbonyl group either at the terminal carbon atom or at the second carbon atom are called carbohydrates. Polyhydroxyketones are organic compounds containing many hydroxyl groups and a ketone group. Moreover, it has 3 carbon atoms and the carbonyl group is at the second middle carbon atom. All the ketose monosaccharides are reducing sugars. Ketose and aldose are monosaccharides which can be differentiated because on the group they contain. A. Aldose is also called glyceraldehyde which has a single asymmetric carbon and thus there are 2 stereoisomers of this sugar. B. Ketose is also called dihydroxyacetone because it contains a keto group, whereas glyceraldehyde is called an aldose because it contains an aldehyde group. Carbonyl compounds are generally divided into 2 groups. One category is composed of the aldehydes and ketones, the other composed of the carboxylic acids and their derivatives. These 2 groups generally differ in their kinds of chemistry and their actions. Polysaccharides. 1. Glycogen. It is a long and branched polysaccharide, glucose polymer, that humans and animals store in the liver and skeletal muscles, main storage of carbohydrates in the body. Number 2, starch. It is available in plants. It is the main carbohydrate of diet. Rich sources of starches include potatoes, rice, and wheat. It is a polysaccharide glucose polymers made up of 1. Amylose, outer layer of starch granules. Molecules are linear, long but with no branches. 2. Amylopectin, inner layer of starch granules. Molecules are long and with branches. Humans and animals digest starch by hydrolysis by the enzyme amylase. Starch is a storage form of glucose in plants. There are 2 forms of starch, amylose and amylopectin. Structurally, they differ in the amylose is a linear polysaccharide whereas amylopectin is branch. Amylose is a polysaccharide made of several D-glucose units. Amylopectin is a polymer of several D-glucose molecules. 80% of amylopectin is present in starch.
Dave explains.
We've all heard of carbohydrates and sugars, especially if we are loading up with energy for the big game or if we're on a diet. But many people don't know that these words refer to the same class of molecules. Carbohydrates got their name because they are literally hydrates of carbon, molecules with several carbon atoms that each bear a hydrogen and a hydroxyl group. When they are small, they are also known as sugars, and their names end in ose, like glucose or sucrose, which is the sugar that we commonly refer to as simply sugar. Let's learn about monosaccharides first. These are the monomeric units that polymerize to form polysaccharides. We can name these according to the number of carbon atoms they have, which will be between 3 and 6. So a 3-carbon monosaccharide would be a triose. If it has 4 carbon atoms, it's a tetrose. 5 carbons would be a pentose, and 6 would be a hexose. In addition, all carbohydrates will have either an aldehyde or a ketone functional group in the molecule, so we would refer to those as an aldose or a ketose, respectively. Combining these conventions, we could refer to this monosaccharide as an aldohexose, and this one as a ketopentose. Each of these carbons, the ones that bear both a hydrogen and a hydroxyl, will be a chiral center, and the convention for drawing linear monosaccharides is to use Fischer projections. When we look at these, it is important to understand that each vertex is a stereogenic carbon, and we show the hydrogens and hydroxyls on either side. With Fischer projections, horizontal lines are implied to be wedge bonds, and the vertical lines are implied to be dash bonds. To remember this, just imagine a bow tie on each carbon, like it's going to the chemistry prom. Fischer projections are just a different way of visualizing a molecule, which we can see if we draw this molecule in line notation and view it from the side. The Fischer projection is what we would see if we were in the plane of the screen looking directly at the chiral center. However we choose to view it, it's important to realize that Fischer projections do not imply a flat molecule with 90-degree bond angles. These carbons are still tetrahedral. We just save time by drawing sugars this way. When we draw linear monosaccharides, we always put the aldehyde or ketone at the top and draw the rest of the molecule downwards, and we report the stereochemistry of the molecule by looking at the chiral center at the bottom, furthest away from the carbonyl. If on this carbon the hydroxyl points right, it's a D sugar. If it points left, it's an L sugar. So we would call this D-glucose, and this would be L-glucose. This terminology is a bit more outdated than the R and S we use to assign absolute configuration, but the convention has stuck around, and it remains the way that we differentiate between enantiomers of sugar molecules. We got this from glyceraldehyde, the simplest sugar, and an aldotriose. This has only one chiral center, and we developed D and L terminology according to the two enantiomers of this molecule. For some reason, nature has selected to work with D sugars, so unless otherwise stated, we can assume that we are talking about D sugars. Let's also note that since a molecule with N chiral centers has 2 to the N stereoisomers, there are 2 aldotrioses, the 2 glyceraldehydes, since there is only one chiral center on the molecule. There are 4 aldotetroses, these 2 and their L enantiomers. There are 8 aldopentoses, these 4 and their L enantiomers, because of the 3 stereocenters, and a total of 16 aldohexoses, these 8 and their L enantiomers. These differ only in the stereochemistry of these chiral centers. Lastly, with Fischer projections, let's be sure to understand that swapping the position of 2 groups on a chiral center results in the inversion of that stereocenter and a totally different molecule. And while 90-degree rotations are forbidden because they invert stereochemistry, 180-degree rotations are allowed. Monosaccharides exist in an equilibrium between a linear and a cyclic form, with the cyclic form being highly preferred. They cyclize by an intramolecular hemiacetal formation, a mechanism we learned in organic chemistry. We know that when hemiacetals form, it's because an alcohol attacks an aldehyde, or ketone. In this case, it's an intramolecular cyclization because the hydroxyl group and the carbonyl are on the same compound. Now, let's orient this linear molecule in a way that we can see the cyclization take place. We know that carbonyl carbons are sp2 hybridized and therefore exhibit planar geometry. So when the hydroxyl attacks the carbonyl, it can do so from either side, thus generating 2 different stereoisomers, which are called anomers. It can either attack from this side, pushing the new hydroxyl down, resulting in the alpha anomer, or it can attack from this side, pushing the new hydroxyl up, resulting in the beta anomer. That makes the resulting hemiacetal carbon the anomeric carbon, because we can either get the alpha anomer or the beta anomer, depending on which side the hydroxyl attacks from. When we draw cyclic monosaccharides, we sometimes use Haworth projections. With these, we look at the ring from the edge, meaning this part of the ring is closer to us and this part is further away from us. And we show the functional groups projecting straight up and straight down. This does not accurately display the true geometry of the molecule, because we know 6-membered rings like these prefer to be in a chair conformation. But Haworth projections have other practical uses. When we draw these, the convention is to place the anomeric carbon on the right, and the CH2OH on the other side of the ring pointing up. If the new hydroxyl group that was generated during hemiacetal formation points down and is trans to this group, we have the alpha anomer. And if it is pointing up, cis to this group, we have the beta anomer. If a cyclic monosaccharide has a 6-membered ring, we will call it a pyranose. But sometimes the hydroxyl on carbon 4 can do the attacking, resulting in a 5-membered ring, which we will call a furanose. Rings smaller than this are unlikely to form due to ring strain. We should also note that monosaccharides don't always remain in the alpha or beta form. We can have an equilibrium between them, since the hemiacetal formation is completely reversible. This alpha glucose might go back to the linear form and then cyclize again to form the beta anomer. In fact, for glucose, the beta anomer is preferred because the hydroxyl on the anomeric carbon will be in the equatorial position versus axial in the alpha anomer. For this reason, a sample of glucose that has more of the alpha form than the beta will undergo mutarotation, which is a shift towards equilibrium values for the two anomers, which in the case of glucose is about 2-to-1 in favor of the beta anomer. A sugar will not always prefer the beta anomer. In some sugars, like mannose, the alpha anomer is preferred due to reasons of hyperconjugation that we call the anomeric effect. So we now know a bit about monosaccharides, their linear form, and the way they cyclize. And it is the cyclic form that is able to polymerize to form long polysaccharide chains. Let's learn about those next. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, Professor